This video is about the basics of circular motion. We'll start by looking at angular displacement, angular speed, period, and frequency, and then discuss the link between angular speed and linear speed. Let's begin with some basic definitions. First, we'll see how these four terms are defined, and then we'll see how they exactly apply to an object in circular motion. Angular displacement is the angle through which an object moves when in circular motion. It can be measured in degrees or radians. Even though linear displacement that we learned about in topic 2 is considered to be a vector, in the IB physics course, angular displacement is only considered as a scalar. Angular speed is best defined by using a formula. It is equal to angular displacement divided by time. Of course, this is the time taken by the object to move through the angular displacement angle. The symbol for angular speed is the lowercase Greek letter omega. We have already learned about period and frequency in topic 4. The basic idea here is the same, because period is the time it takes for the object to go around the circle once. As we've seen earlier, the symbol for period is uppercase T. Frequency is best defined as 1 over the period. We have also seen this formula in topic 4. The symbol for frequency is lowercase f. Let's see how to calculate these four quantities through an example. We have an object that moves in uniform circular motion and completes a quarter of a full turn in 2 seconds. Uniform circular motion simply means that the object is moving at constant speed. Let's draw this situation. The object moves from point A to point B in 2 seconds. Let's label the angle through which the object has moved as theta. This angle is the angular displacement. Since the object completes a quarter of a full turn, theta is equal to 90 degrees or pi over 2. It is a bit more common to use radians in physics, so I will use radians here. The angular speed, omega, is equal to the angular displacement divided by time. The angular displacement is pi over 2 radians, and the time is 2 seconds. Dividing by 2 is the same as multiplying by its reciprocal, so 1/2, which gives us pi over 2 multiplied by 1 over 2. This is equal to pi over 4, and since we divided radians by seconds, the unit here is radians per second. Since it takes 2 seconds for the object to complete a quarter of a full turn, a full circle requires 8 seconds. Therefore t, the period, is equal to 8 seconds. The frequency is 1 over the period, so we get 1 over 8 Hz. The unit of frequency is the same as we learned in topic 4. Next, let's see the link between angular speed and linear speed. Let's assume that we have a circle of radius r, and that an object is moving around this circle with angular speed omega and linear speed v. We'll also assume that the period is t. The circumference of the circle is equal to 2 pi r. The linear speed is equal to distance traveled over time. During the period, the object travels around the circle once, so it covers a distance of 2 pi r. Therefore v is equal to 2 pi r over t. Rearranging this equation, we get that t is equal to 2 pi r over v. For omega, the angular speed, the angle completed in one full turn, which is 2 pi, divided by the time it takes to complete a full turn, which is the period. Again, rearranging this equation gives us that t is equal to 2 pi over omega. Equating these two expressions, cancelling 2 pi and rearranging for v, we get the following formula. And here are the variables in this formula. Let's summarize what we have learned in this video. We began with some basic circular motion definitions for angular displacement, angular speed, period, and frequency. Then, in the second part of the video, we examine the link between angular speed and linear speed. Here is the formula connecting these two quantities, and these are the variables. This completes our discussion of circular motion basics. In the next video, we'll learn about centripetal acceleration and centripetal force.